Hello everyone. And myself Arshid Mukunda. So in this video we'll be walking through our project, which is AES-128 hardware and software co-design, which is implemented on the DE1-SoC FPGA. So coming to just the brief description is that I just show how FPGA hardware accelerates encryption while software handles validation, offering a flexible and efficient approach to secure encryption. So we'll just dive into the slide one, so which is our project objective and motivation. Uh, so again, we just developed a part of design and analysis reconfigure system course. So this was included in the course. So and then uh, coming here, this is my teammate, also known as Ashit. So his full name being Ashit Navin Rachappa. So coming to this slide, our objective for our project was to create a full AES-128 encryption system using our DE1-SoC hardware and software co-designs. So the motivation for this project was the cryptographic algorithms like AES are computationally demanding. So with this, the FPGA, we can speed up encryption by leveraging the parallelism by implementing new computings, and then the ARM processor handles the flexibility of software, making it easier to test and validate. So and also coming to the system design for this, so in our design the HPS manages the control, and then there's also a key generation and validation while FPGA accelerates the encryption process. So our key goal was to verify the FPGA output by comparing it with the software results, so which I'll also be demonstrating later part of the presentation. So we'll just dive into the slide 3. So this is the overall system architecture. So if you just look at this, this is the user input. So this is where the user inputs plain text through a UART terminal connected to the HPS, and then this is the HPS role. So this ARM processor generates the AES key and performs software-based encryption and decryption, and it also manages communication with the FPGA. And then and in this, the FPGA role is uh, that the FPGA contains the dedicated AES-128 core performing the encryption and the process, and then the communication is that the HPS and the FPGA communicates via the lightweight AXI bridge. So this uses the memory mapped registers. So this is where the data are being shared to each other. So then coming to the HPS software design. So this has mainly 3 points, which is like software features, communication with FPGA, and verification. So coming to the software features, the software generates a random 128-bit AEC key and accepts up to 16 ASCII characters as a plain text. So and then this is sent to the SPS processing and verification uh, field, but with the FPGA with the AXI low bridge where the data is being sent with the memory mapped registers. So and then this communication with the FPGA. So the HPS writes data into registers and retrieves the ciphertext after encryption. And then the verification goal is that after encryption, the software compares the hardware output with the software result to verify the correctness. So this verification goal, it receives the ciphertext from FPGA again, and then it verifies if both are matching, and the result will say yes if both are matched, so it will give a pass. If it is failed, it will give us failed. So coming to the next slide, which is so this is the FPGA AES hardware design. So So in this, this basically just tells that the AES-128 encryption core implementation in the Verilog, and then the core features that we have used is 128-bit key input, 128-bit plain input, plaintext input and 128-bit ciphertext output. So this is where the core is being happening. So in this the inputs are being given. So and then this is what I've also uh, explained it in the previous slide. So this is where the inputs are coming in, and then cipher text bit output, and then key text cipher and start to status handshakes. These are all happening through the AXI low bridge of the HPS. So coming to the hardware, software communication and memory mapping. So in this, we have a communication method, which is the HPS and FPGA communicates through memory mapped registers, as I've already mentioned, which is the lightweight AXI bridge. And then the data flows through the ASCII key and the plain text are written into dedicated registers. A control signal is used to trigger the encryption process. Once the FPGA finishes, it finishes the encryption. So it sets a status flag. So if you just look at this, this is the status flag, and then these are the keys, plain text registers and ciphertext registers. And then coming to the synchronization part of this, the HPS continuously checks the status and reads the ciphertext only after like encryption completes. So you just look at this. This is how the verification is happening. So in this, if you just look, the HPS waits for the FPGA completion using polling-based synchronization. So it ensures the correct timing between hardware execution and software validation, so that there is no mismatch with the timing. Because if there is a mismatch and then if a cycle is missed, then there are higher chances of the matches being failed. And then this is the verification strategy. So we use a two-level verification strategy to ensure correctness. So first one, the 11 one being test vectors. So I've tested the FPGA output against 7 standard AES-128 test vectors. So from the NIST FIPS 197 and SP 838A. So this 7 vectors, I've just added it to my main.c code. So in that, I'm just uh, giving it to the board saying that just verify for these 7 test vectors first. And then I have also added the level 2, which is interactive user testing. So in this, I've allowed users to provide custom plain text. So it will also ask a prompt saying that do you want to use the interactive mode. So I've if I give S or Y, so it enters into this level. So in this case, we use the software AES output as the reference and compared both hardware and software results. And then coming to the results and demonstration, all 7 test vectors were passed successfully, and then for every test case, the FPGA ciphertext matched exactly with the software AES output, and then the decryption always recovered the original plain text, which is to be done. So, and then the interactive testing, coming to that, we also tested with custom user inputs, and once again, the results were perfect. So, and then I just this also confirms that both the hardware and software code design is functionally correct and reliable. So this is the terminal output that I've taken from the putty terminal. So this is the mode that I've used. So I just go into the USB drive and then I just execute the file, and then coming to this, it starts encrypting. So it initially runs the known 7 test vectors, which are already written in the C code. And then, so once they're all passed, it also asks for the user to give the interactive mode, which says, do you want to enter it? So if you give Y, and you can see that the user, which is me, I've entered Ashit uh, 3 FPGA, so it has also passed. And then again, if you give no, it says it goes for exiting. And then I'll just give a demonstration for this. So as we have seen the results, so I'll just do the demonstration. So I'll just exit the PPT and then I'll just turn on the board. And then I've already connected my USB pen drive to the board, and it has already loaded the executable file. So I'll just open Putty. So I've already saved the project, so it should be running. So we'll just log in inside this, and then these are the commands that we give. So let us just check. So this particular file is in the device which boots SDA1. So we're just gonna mount it. I'll just copy paste these commands so we save some time. And then I just dive into the drive. So the directory for where USB drive is. So we just look at this. So if you just look, this is the file that is inside this directory. So we just keep it ready. So before executing this, we will have to program the FPGA board with our RTL code. So once this is done, we just hit start. And once this is successful, so we'll just go inside this. And then you can just look at this. So we just executed the file and it is running 7 vectors. So this is a vector 1, vector 2, vector 3, everything is passed. And then after once all the 7 vectors are passed, this asks, do you want to test your own plain text? I just give yes. So I'll just give Ashit G FPGA close. So you can just look at this, the interactive test. This is the plain text, this is the key, this is the hardware cipher, this is the software, this is hardware decrypt, and then software decrypt, and then it has done everything. So and then if you just give yes again, so you'll be able to mm, enter any of the text. So I just enter I loved this FPGA. So again it passes. So we just cut it down. So I just give no. So and then it just exits the terminal or the programming part, and you can again run it if you would like it. So I've also attached these screenshots in the presentation. So if you just look at this, these are the same screenshots that I've attached. And then coming to the conclusion, so I conclude that we successfully implemented AES-128 encryption with the hardware or software co-design on the given DE1-SoC FPGA board. So the FPGA accelerates encryption while the HPS handles control validation and decryption. So the verification part was that we verify the systems using both standardized test vectors and the custom user inputs, with all tests being passing. And then there's also a scope for future work, which is we plan to, in case we work together, so we are planning to extend the FPGA design to support AES decryption. And then we are also considering adding additional encryption modes like CBC or CTR, and then concluding performance benchmarking. So we are just trying to improvise the performance using these techniques. And then we also would like to compare the hardware versus software speed. So we would just use these modes for encryption, and then we'd like to compare the test results against the uh, already available test vectors or uh, results. So and then this is it. So thank you for watching our presentation. This concludes our demonstration for our FPGA project, which was using these AES-128, the hardware and software co-design on the DE1-SoC FPGA. And we appreciate your time and hope this project gives you some insight into the power of FPGA accelerated cryptography. So, thank you.